All right, so yes, my great pleasure to have Karen now presenting. So I take it that you are kind of co-presenting?
Yeah.
Okay, well, looking forward to see you.
Thanks. Yeah, so it's just some new ideas that I've had in the past week, and Marta and I were discussing them too. So we made the slides together. I'm just going to talk, basically. But yeah, it's coming from my broader project, which I think you're all familiar with by now, where I'm really interested in kind of getting some constraints on QG or trying to understand more like why we're even looking for the theory in the first place. Because of course, normally when physicists look for a new theory, it's because they've observed some phenomena that needs explaining. And that's not the case in QG. So I'm like asking, why are we actually looking for the theory? Can we find some principles based on these motivations that can help us kind of understand better even what we're looking for, understand the form of the theory a bit. And then, of course, Niels and I have worked on this too, looking at the principles of quantum gravity. So yeah, looking at some of these principles, of course, I was looking more at correspondence, previous work, and emergence, because I thought that was like the most basic constraint on QG that doesn't motivate it, but it's nevertheless like the one everyone agrees upon, that the new theory, whatever it is, needs to appropriately match up or recover GR in the appropriate limit. But then I realized, no, there must be the actual most basic principle on any physical theory is consistency. So yeah, started thinking about what is consistency in the context of QG. But yeah, fitting into this broader project. So yeah, we'll start off saying a bit about consistency, what it is, and then an example being the Bohr atom as a kind of classic inconsistent theory that people have discussed, which is particularly interesting because it's often used as an analogy in motivating QG as well. And then, so consistency can be used both as a motivation for theory as well as a constraint. And as Marta and I have worked out, it's not exactly matching up between the motivations and the constraints. So we'll discuss this. So, okay, consistency. It's, of course, not just a constraint in physics or science, it's really used in philosophy. Like when we're trying to work out our theories of philosophy, how do we judge them? Well, if they're inconsistent, then you kind of think, well, we've got a problem, something to discuss. And from the very beginning, right, like talking about the very ancient Greeks, and they were coming up with all these paradoxes. So it seems like it's very central to philosophy as well. And yeah, when we've got an inconsistent theory, whether in science or philosophy, it's usually taken as a sign that something's gone wrong. And Popper was really emphasizing this, and many other people have too, that consistency can be regarded as the very first of the requirements to be satisfied by every theoretical system, be it empirical or non-empirical. And why is this? Well, Popper really pointed out if we were to accept contradictions, then one would have to give up any kind of scientific activity. I mean, the complete breakdown of science. Because it can be shown, of course, in classical logic, that if we have two contradictory statements, then you can get any statement whatsoever, because you can validly infer anything. And so he says a theory which involves a contradiction is therefore entirely useless as a theory. So, I don't know, the first slide I had up with the two blobs, it's meant to be like a logical explosion here when you bring these two things together and they're inconsistent. It's supposed to explode. So yeah, and I'm following Vickers' book on this as well. So according to classical logic, an inconsistency leads to the contradiction, and any statement follows from the contradiction. So it seems like this death knell for any physical theory, if we can use it to predict anything, right? And yet, philosophers since then have gone through the historical record and pointed out many kind of cases that they take to be inconsistencies in previous scientific theories. So scientists don't just reject inconsistent theories. And Vickers argues too, and other people as well, that we shouldn't, in fact, reject them, that they can still be useful and applicable. So how do we avoid this logical explosion? Well, even if we have an inconsistent theory, in most cases, scientists don't use all of the propositions at once in any piece of reasoning. They'll just collect a subset or work within a restricted domain, and they'll just avoid deriving these contradictions. Also, as Vickers points out, many cases of what we think is inconsistency is actually just an implausibility. Like, it's difficult for us to make sense of, it's counterintuitive, but it's not like an actual inconsistency. So there are three main forms of inconsistency in science. Firstly, we have inconsistency between theory and observation. I should say, I don't think Priest or Vickers uses that term. I've just put it in to give these labels, empirical inconsistency. We also have external inconsistency, which is when we have two different theories and they're saying contradictory things about the world. For instance, in physics, using kind of different descriptions of matter, and also theories in different sciences giving us different descriptions of, the same world. And finally, there's cases of internal inconsistencies. But here it's like harder to find non-contentious examples. There's so much written on inconsistency in science, in the general philosophy of science literature. And it seems like they just kind of debating, like, is this inconsistent? How do we reconstruct this theory? Blah, 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 blah. So I haven't found it that useful for my actual project, which is trying to use these inconsistencies and, what do we do with them? The heuristic use of inconsistency. I haven't found so much. It's more like they're just debating, do scientists really employ inconsistent theories or not? And that one, I'm not so interested in. Okay, so each of these types of inconsistency plays a role in the search for quantum gravity. Some of them being used as motivations for the theory, and others being taken as constraints. And sometimes the ones from the motivations get turned into constraints, as we'll discuss. But also, I want to say that these are appearing in ways that are kind of different to previous cases of inconsistencies in science, or at least according to that general philosophy of science literature, because they're really interested in looking at theories as sets of statements, and are these statements in contradiction with one another? Whereas in the case of quantum gravity, what I've seen is a lot of the physicists, for instance, Hossenfelder, in responding to Niels and I's paper, she said, if we have, perturbative GR and it's not UV complete, she says the theory is then self-inconsistent. She actually uses this word, for instance. And other physicists too, they take these divergences in the theories to be inconsistency, internal inconsistency. Also, so that's with the internal inconsistency. Also, there's empirical inconsistency, but as we'll argue, it's kind of an unobserved one. It's not like these previous cases where we actually have experiments and phenomena that are disagreeing with the theory. So we'll go into explain that. So just quickly on this Bohr theory of the atom to show this historically inconsistent theory. The theory was incredibly predictively successful. Bohr proposed it to explain the hydrogen spectral lines, but then it turned out to also predict them for helium to quite good accuracy, like 5 decimal places. So after that, everyone, Einstein as well, was really convinced, well, this is a good theory, must be correct. And yet it was widely claimed to be inconsistent, even by people in those days. Vickers goes through all these claims and tries to work out, well, is it really inconsistent? Where does the inconsistency lie? And he argues that there's no internal inconsistency because here. He lays it out in these three propositions and then argues that there's no contradiction entailed by those three propositions. But the more pressing inconsistency, I guess, the one that more people are worried about, is not that internal inconsistency, but an external consistency. So it conflicted with Maxwell electrodynamics. Because if you have this picture of the atom, basically, with the electron orbiting around, electrodynamics predicts that the electron will eventually, is radiating, and it will eventually fall down into the nucleus because it's losing energy, and at some point you get an infinite force. So there's two things. There's this contradiction with the electromagnetic picture, and there's also this infinity that pops up. So yeah, people taking this as really bad inconsistency. It's nonsense. Maxwell's equations are valid under all circumstances, and an electron in orbit must radiate. The theory is in greater or less contradiction with ordinary mechanics and electrodynamics. So quantum mechanics and then developing on this theory, of course, solved these issues. Firstly, by just rejecting this picture of an electron orbiting the nucleus. Also confining the electron to discrete energy levels, of course, and allowing it to emit only discrete levels of energy. And also by having this lowest energy state, so Bohr radius, so it never falls in and you don't get these infinity anymore. So what the example shows is that inconsistent theories can be successful, but also that kind of removing the singularities and resolving the inconsistency, the external inconsistency, can be heuristically useful, so in developing quantum mechanics. And this particular example, as I said, it's also widely used in the motivation for QG. There's this idea that we've got these infinities popping up in GR and QFT, so maybe gravity should also be quantized in the same way that we quantize the electron. Maybe quantum gravity also has a discrete spectrum. But we'll kind of want to press that infinities actually aren't inconsistencies against what all these physicists are saying. It's not really an inconsistency in the sense of the way philosophers would think about it. Yeah, and we'll see it in the case of GR and QFT. The infinities in our current theories don't necessarily mean that the theory is inconsistent or incomplete. So yeah, the relevant inconsistency there was with the Maxwell's theory, the external inconsistency. All right, so now motivating quantum gravity, the external consistency, internal consistency, and then I'll give a bit of a digression on singularities, because I think physicists just tend to hate them. So yeah, as stated, normally we're motivated by observed empirical inconsistency, and this isn't the case for quantum gravity. Instead, the very primary motivation for the theory is an external inconsistency. We've got GR, we've got QM, and trying to put them together, they're saying conflicting things about the world. And so we think we want this deeper theory of quantum gravity. But there's also apparent main motivations coming from what physicists are promoting as being internal inconsistencies in GR and QFT related to singularities. So I'm going to look at those and kind of argue that the singularities themselves aren't necessarily inconsistencies and may not necessarily prompt quantum gravity based on that. There are inconsistencies in our current theories, but they're the ones that actually aren't usually taken to motivate quantum gravity. And yeah, kind of arguing that the real problem with having the infinities is due to the idea that we don't observe infinities in the world. So that's kind of that will be the argument there. Okay, So yeah, this one I think you all know by now. Both GR and QM are supposed to be fundamental universal theories, applicable to all energies at all scales, and yet they say conflicting things about the world. They give us conflicting pictures, which we can luckily ignore for all practical purposes. The theories are very, very successful on their own, as long as we're applying them within a restricted domain. But of course, we're expecting to need both for some particular domains, in particular the interior of black holes, early universe cosmology. And so this external inconsistency between the two is really motivating the new theory. And it gives us some preliminary constraints. The new theory, QG, should somehow take into account insights from both. And it should be applicable in these domains where we expect quantum gravity to apply. We're expecting both theories to be necessary. So yeah, it does lead to some constraints as well as being a motivation for seeking the theory in the first place. So yeah, some of the conflicting pictures, but I think we'll really need to go into these more detail and actually see what principles in QG and GR are in conflict and whether it's an inconsistency or not too. So why is this motivational? Basically because we like explanation. If we're looking for a fundamental theory, we want a coherent picture just for our own explanatory benefits. And yeah, it can be heuristically useful. We're really stuck. So maybe these inconsistencies can give us some idea on where to look for the new theory. It gives us problems to work on. Kind of thinking about which assumptions might need modification. So perhaps the continuum properties of space-time, background independence, and so on. So yeah, that's the external inconsistencies. We'll now move to the internal inconsistencies. So these are within GR itself and within QFT itself. These are taken to suggest that maybe our current best theories are somehow incorrect or incomplete. And yeah, a lot of physicists are pointing at these space-time singularities. So thinking about GR now, internal inconsistencies with GR, this idea that maybe these space-time singularities indicate that the theory is incomplete. But is that an inconsistency? So it's also very hard to make sense of in what sense does the space-time singularities indicate that the theory is incomplete. So in discussing geodesic incompleteness, Curiel and Ehrman have been really pushing these pictures, saying, well, how is it incomplete? The theory is applying at all points in space-time. There's no kind of missing points. Singularities, they're not located anywhere. So how is the theory being incomplete by failing to describe what happens there? Ehrman even goes further in taking these singularities as being prediction of GR. Yeah, so there's no singular points of space-time where the laws of GR fail to apply. And Ehrman's really following on by a paper from Meissner here, who argues again that there's no reasonable point at which to anticipate a failure of the theory. So the space-time singularities themselves don't necessarily, or at least not clearly, indicating an incompleteness or an inconsistency of GR. Where does the inconsistency come from? Like, what's the actual problem here? It's the indeterminism. So geodesic incompleteness means that particles could pop in and out of existence right in the middle of a singular space-time, and that space-time itself could simply come to an end, though no fundamental physical mechanism is bringing it about. And this is really the inconsistency here. Ehrman says, GR is a deterministic theory. We're using it to describe deterministic universe we observe. So if we have geodesic incompleteness, And there is a breakdown of predictability in this sense. And that were visible to us in a theory that we've set up to be describing the deterministic universe we observe, then there is an inconsistency here, and a quite bad one, because the laws are just perversely undermining themselves. So the singularities themselves aren't the problem, it's the indeterminism.
And, I mean, this is actually a good example of what we mean with internal inconsistency, in the sense that in theory, like, assume something or state something, and then the same, I mean, internal to the same theory, you have like this problem of having a contradiction. So it's really like, so this could be a good example of the kind of example we wanted
like
to
a real inconsistency.
Yeah, a real internal inconsistency, right? Because you have a theory that is supposed to be deterministic, and then you have like this kind of indeterminism that, of course, is in contradiction with what we just said. So
Exactly. So, is this taken to motivate quantum gravity? Well, it really relies on the fate of strong cosmic censorship. So I've just copy-pasted a lot of words here, I'm sorry. So the idea is that somehow you can just avoid, you can nullify these violations of predictability by making them, or ensuring that they're just not detectable, even by local observers. So basically you're falling into the black hole, you're not observing anything, and then you pop out of existence. That's it. Like, you don't know that you popped out of existence. No one does. And so then the lack of determinism is no longer problematic for the theory, basically. So that's the Penrose strong cosmic censorship. I won't read all of that. Right. So if this inconsistency indicates that GR is incomplete, if it does motivate quantum gravity, what about if strong cosmic censorship does hold? I mean, we don't know. Would we lose the motivation for QG here? So, yeah, I haven't seen this put forward as a motivation for QG, even though it's, as we said, the most striking example of inconsistency in GR, internal inconsistency. There's one more argument that I put forward with the paper with De Harrow, but actually De Harrow came up with this one himself. Not that I'm blaming him, it's a good argument. But here discussing curvature singularities rather than geodesic incompleteness. The idea basically is that we're constructing an effective action for GR, including higher curvature terms, which we can normally neglect. But as you're approaching a curvature singularity, you can no longer neglect them because the terms are getting bigger. And then GR itself is no longer a good approximation. So then you could have an inconsistency between GR and the expected quantum gravitational effects near the curvature singularity. But this one isn't an internal inconsistency. Maybe it's an external inconsistency, but we're saying maybe it's actually an empirical inconsistency, but one we haven't observed. Curiel has responded in talks to this argument, just to say that, yeah, sure, this happens, but it doesn't have anything to do with the singularities themselves. And I think, okay, that's actually a fair response. It doesn't actually have to do with the singularities, but a conflict between the two pictures. All right. So, yeah, that's the kind of basic argument that our relevant internal inconsistencies might actually be unobserved empirical inconsistency, but still can be challenged. Moving on to the internal inconsistencies in quantum field theory. You often see, lots of papers saying, there's a lack of mathematical rigor. We have these perturbative divergences in QFT. Are these the inconsistencies? Actually not. Kind of pace some of these physicists that are saying that the lack of UV completion means that the theory is internally inconsistent. In philosophy, we don't take that as an inconsistency. It's not real internal inconsistency. The actual internal inconsistency in QFT comes from Haag's theorem, which I haven't looked into, but it is basically starting off, you have to have the system being a free system, but then you introduce this interaction picture because you want to describe interacting systems, and so you're conflicting with your original assumption. So that's an internal inconsistency in QFT. But again, when is this ever used to motivate quantum gravity? And it could, but it could just as similarly motivate you looking for AQFT or other theories. So yeah, this is open. Okay, so just have a brief digression on singularities here. Because, yeah, I believe we've shown that infinities don't necessarily signal approximation, incompleteness, or inconsistency in your theory. I mean, they can, but not always. And yet, I think physicists just really hate infinities. So I've come up with this word, kind of like, what was it, the horror of the vacuum? Now we've got the horror of the infinite, horror infinitum. So, for instance, Ellis, Meissner, and Nikolai have this paper against infinity, arguing that infinities lead to paradox, and we have this strong conviction that infinity just can't exist in the world. And so if our theories have it, then we're in trouble. These can't be physical theories. And they take it as strong motivation for QG to get rid of the infinities in our current theories. And particularly, yeah, again, with this Bohr atom analogy, they think that maybe having discrete space-time or quantized space-time is a way of avoiding the singularities, and this is the way forward. So they say the apparent contradictions and inconsistencies we encounter when we try to extrapolate known theories to arbitrary large, arbitrary small distances are widely taken as an indication that the assumption of a space-time continuum ultimately cannot be viable. Unfortunately, they don't really say they mean by widely taken as. They didn't give other references here, so I guess it's just their feeling as a community. Hossenfelder, she's a bit more reserved on this point. She's written that paper about the minimal length, but not putting this forward as a motivation for it. Instead, I've watched some of her recent videos, and she says why infinity is problematic is that we can, by definition, we can never observe it. It's beyond measure. And so she thinks that's just an unscientific concept to have in your theory, something you can't measure, so we can't have it. But yeah, our response to this, we've got a few points. First, to point out again that here we're not taking the infinities as an internal inconsistency. They might be an empirical inconsistency. If we can't test it or see it in the world, then we have a contradiction between our theories and the world. But also, thinking about this too, like, why does everything that features in our theories have to directly correspond to something in the world? Couldn't we have infinity in our theory and yet not be necessarily having to map on to something in the world? So we're thinking we could have it in our theory so long as it's not really being an observable quantity or prediction. Those we've seen, some might take the singularities in GR as a prediction.
Yeah, I mean, the idea of having map, like a very direct and limited map between the stuff that we have in the theory and the world is kind of naive scientific realism that, I mean, I'm not sure like everyone would like to endorse actually, because you should really try to explain everything in the world with your theory and vice versa. So it's kind of a weird correspondence that you don't have to endorse.
Yeah, like who wants
And
to
in
endorse
the case of infinities, as long as they are like in the theory, but they don't have any direct implication with something that you have to measure to empirically confirm the theory and stuff like this, that should be fine, right? So in this way you can also avoid the empirical inconsistency, because you have the infinities in the theory, but you don't, I mean, if they are not involved in the measurement or in the empirical confirmation, it should be fine also with empirical consistency.
Yeah, but still recognizing that, resolving inconsistencies or idealization assumptions, things like this, has been historically useful. So maybe as a motivation, getting rid of them is okay, but then what about as a constraint? So I'll turn over to you now to do this last section on constraint. Thanks.
So yeah, first of all, we find this distinction between the kind of constraint that we have in QG. So we have some constraints that are derived from the previous theories. So we just present the kind of inconsistency that you have. So the internal, the external one, and stuff like this. And this inconsistency kind of constrains our quantum gravity theory, because we have to get rid of that, right? We don't want to carry on this inconsistency in our new theory. We want to, well, we'll talk about this later, but we kind of want to find a solution for these inconsistencies. And then the second kind of constraint are given by inconsistency in the new theory. So we don't want to have new inconsistency in the new theory, and we want to avoid empirical inconsistency and also internal inconsistency. And well, in the case of quantum gravity, if the theory is supposed to be a fundamental theory of everything, in a sense, the external inconsistency collapses into the internal one, because you don't have any competing theory, right? So you just have, I mean, the theory should be consistent in itself, in a sense. If it's a theory of everything, you don't have to worry about other theory, right? So this also is a kind of constraint. So the two consistency have to match up, let's say. So, well, the constraints derive from external inconsistency between GR and QM. So we saw this before. The new theory must take into account the insights of both theories, and in the sense it should be like it should conciliate the two theories. It should make sense of. It should give a physical picture of the world that makes sense of both what we observe in GR and in QM, and it's coherent in itself. And then we have, it should explain what happened in the domains in which we have both gravitational and quantum effect. So it should be applied in those domains. And then we would like also to recover space-time as an approximation of GR. So we have also like these correspondence relations that in a sense are an empirical they are a constraint given by empirical consistency, because we want our new theory to be consistent with the observation that we have up to this point. But also, in a sense, it's an external consistency, because it's you should have this correspondence with the old theory that we have. So with quantum mechanics and general relativity. And so the internal consistency, well, we talked about it before also, and the point is, should really quantum gravity resolve the singularities in the previous theory? So this is kind of an open question. The idea is that we want a fundamental theory, so it should be complete in a sense. So we would like to avoid singularities or this kind of stuff. And again, also, like we said it before, so we would like to get rid of singularities, but it's really so bad to have infinities or these weird quantities in our theory.
Yeah, if they don't signal incomplete.
Yeah, yeah, exactly. So yeah, the important point is that if our theory is a fundamental theory of everything, again, it shouldn't be complete, because otherwise we have this logical inconsistency between, you know, theory of everything and then it's kind of limited or incomplete. That's bad, which we should avoid that. So that would be an internal inconsistency in the case of Qt. And then also like, well, it's very likely that we would like to have UV completion, because
otherwise we feel like there's something else beyond.
Yeah, it's just, yeah, exactly. Otherwise that's kind of would signal that still we don't have like our fundamental theory. But we should, you know, find something else. And then, yeah, empirical consistency. So that's not, at the beginning we say that's not really a motivation for finding a theory of quantum gravity, because it's not like we observe something, I mean, that we cannot explain if not with quantum gravity. It's more like a constraint in the sense that, I mean, it's more a constraint in the sense that once we have the theory, it should avoid empirical inconsistency. So in particular, we identify 3 types of empirical observation that can cause empirical inconsistency. So the first thing is that it should explain like, yeah. So the first thing is that, like, it's a question. So should it explain things that we have now in physics and are not explained by the previous theory, or not? Well, once again, the idea is that if it like the theory of quantum gravity is the theory of everything, yeah, then yes, we should really find a way to explain everything. So also like dark matter, dark energy, and stuff like this. Otherwise, we will have an empirical inconsistency, and also an internal one. But then that's kind of an open question. So there are like these empirical observations that are not explained by our current theory, and maybe this observation can act as a constraint on our theory of quantum gravity. And then the second kind is observations that are actually explained by current theory, and we want to preserve these observations. So we want to be able to explain these empirical results with our new theory of quantum gravity. So we should have this kind of correspondence, at least empirically speaking. So once again, the idea of the emergence of spacetime, and to explain the result of the standard model in QFT and quantum mechanics. And then the last thing is that maybe in the future we will have like some new empirical observation, and it's of course like if we want to preserve empirical consistency, this future observation will act as a constraint on our theory, in the sense that they have to be prediction of our theory. So we're open to a possibility of kind of quantum gravitational phenomenology, and of course this will be like a strong constraint on our theory of quantum gravity. Okay, so well, to conclude, this is a kind of a summary of our points. So the first thing is that the primary motivation for quantum gravity are external inconsistency. So we mess up the color.
Yeah,
it should be green, right? external inconsistency. So the inconsistency that we have between quantum mechanics and general relativity. And this inconsistency also acts as a constraint on our new theory in the sense that we want to, conciliate the two theories. But then we have also like different kind of inconsistencies, so in the internal one and the empirical one, and we also want to, and also like this kind of other inconsistency are important, either as a motivation or as a constraint or as both. And another interesting stuff is the thing we say about singularities and how maybe like they're better understood as kind of an a possible empirical inconsistency with between the theory and the world, and not as really an internal inconsistency of the theory. And that's it.
Thank you very much. Okay, so Sam, Chris, James. Yes.
Thanks, this is really interesting. So I just want to ask about, so it seemed like you think that it's okay to have some inconsistencies in your theory, but sometimes not. And I'm just wondering how you tell which are the good inconsistencies and which are the bad ones for the purposes of developing a new theory.
Yeah, it's just, I think if you have a fundamental theory, you wouldn't want inconsistency.
See, that's what I wasn't sure about. So, like, why should the fundamentality of the theory matter to whether you accept the inconsistency?
Yeah. We were thinking about this too, and we think it's just explanation. Like, you're expecting a complete explanation, and if there's inconsistencies, you'll keep working at it. Right?
But
you
why?
wouldn't stop.
So like, why not allow that your sort of most explanatory theory at the fundamental level has inconsistencies in it, and that's just like the best you can do.
Yeah.
And it's like that's as far as it goes. Like I guess I feel the pull of like trying to like iron out inconsistencies. Like I can kind of see why you might want that, but like why the fundamental non-fundamental distinction should matter.
It's definitely I think something interesting to think about. And I don't know if, do we have a reason? No, I just think physicists wouldn't stop. They wouldn't treat it as a fundamental theory.
Yeah, there is a problem of logical explosion. So in a sense, if you have inconsistency in your theory, and the best, the best you can do, you in a sense, strictly speaking, from the logical point of view, one can derive everything from your theory, and you don't want that. Then for the practical purpose, scientists can just take some part of the theory, so some limitation and stuff like this. But then, logically speaking, it's something that, I would say I don't want it.
I'm not super sympathetic to the logical point because there are lots of strategies for dealing with inconsistencies logically. So if you use first order classical logic, it's going to blow up. But that is so much the worse for first order classical logic. So there are lots of strategies that you could use to handle the logical explosion issue.
Yeah. So no, I agree. It might be that the fundamental theory just is inconsistent.
Yeah.
And that's the best we can do.
Can I just say one just a little suggestion? So you could have an inductive argument here. It's the best progress we've made in science in the past has been by trying to wipe out inconsistencies from theories that we took to be fundamental to find new fundamental theories. And every time we've done that, we've developed and we've made science better. And so you could run that kind of argument for why it matters at the fundamental level, but not at the non-fundamental level.
Alright, I'm going to write this down.
So James wants
That
to
one's for
follow
you.
up.
I was just going to make a point about different logic, so.
Okay.
All right, so Chris.
Thanks. I have a comment and a question. So the comment why in the paper by Ellis, Meissner and Nicolai, they don't give a reference but just sort of assert that it's commonly thought as. It's like, when you say, well, the earth is round, and you don't go and dig up the references for that. It's because it's full. Everybody knows this is trivially and obviously true. It's evident to everyone in the field, so there's no need to go and find a reference to that. If you look for references of physicists making the same statements, I'm sure you'll find many. And I bet that none of them will make a reference to somebody else who said the same obvious point. Maybe the most famous one is, Berkman, who in 1980 had this statement that singularities are intolerable from the point of view of classical field theory because the singular region represents a breakdown of the postulated laws of nature. I think one can turn this argument around to say a theory that involves singularities, that involves them unavoidably, moreover, carries within itself the seeds of its own destruction. And sometimes that statement is referred to, but I think it's not because he was the one who came up with the idea. I think because it's a very pithy statement, that's why it's cited. So that's just a comment about that.
Yeah.
The question I have is really about the case of indeterminism in GR.
Yeah.
You identify that as an internal inconsistency between some sort of supposed statement that GR is a deterministic theory and some failure of that determinism. Therefore, that's inconsistent. But I don't really think that there is an inconsistency. Presumably the basis for thinking that GR is a deterministic theory, like Berman does and other people, are uniqueness results. The uniqueness result by Garrosh and Jacques-Briard, for instance, from the 1960s, or similar results. These are theorems of GR, but as every theorem, they come with, under those conditions, the following will be the case. If these things are the case, then we will have a unique evolution, and so on and so forth. And I don't think that that actually is, strictly speaking, an inconsistency. That you find somehow that this statement is not, is contradicted directly by some other problem of incompleteness or some failure of determinism. I would be surprised if you really strictly can do that.
So this might not be a problem, is what you're saying?
I think it's there may be a perception of an internal inconsistency, but if you actually look at it very carefully, it's just because you haven't been careful to state exactly under which conditions you can have a deterministic evolution and under which ones you don't.
Sure. Okay, thanks.
Yeah, that's my sense.
I'll look into this more. Yes.
James, and then Lorenzo?
I think my question actually leads on from this. So another place where internal inconsistencies seem to feature in the context of discovering quantum gravity is in string theory, where theorists will say, on pain of mathematical inconsistency, I've got to set my theory on 26-dimensional manifolds. And it seems to me that this is more clear-cut than the cases that you were indicating, because it's harder to avoid mathematical inconsistency than, well, yours are kind of conflicts with your favourite metaphysical principle, like determinism or whatever. So I was wondering if you could comment on the comparison between the cases.
Yeah, I hadn't thought about it that way, because I think that was kind of going to be the next part of the project, to look at how it's actually used in particular theories, right? So we haven't thought about that. It relates a bit to the question of mathematical rigor, which isn't really consistent, but they're really taking that as another thing. Like, we keep working on it, we're making it much more precise, rigorous than even physical theories kind of need to be. I think this is a really interesting point. Like, should this be used as a constraint or not? But maybe there you can treat it as a prediction, right? We're predicting these extra dimensions coming out of this theory. So it seemed like you would want to keep that in. It does seem like it's being useful there.
Yeah, I agree with that.
What do you think?
Yeah, eventually it could be like an empirical inconsistency if you treat it as a prediction.
Yeah.
In the sense that, I'm not even sure, because how can you actually, empirically test that kind of stuff?
Unobserved empirical inconsistency. Yeah.
Maybe another example is like shape dynamics, where the theory is inconsistent unless you set the overall angular momentum of the universe to 0.
Okay.
and doing arbitrary sets of prediction of the field.
Yeah, okay. This is good. Thanks. Okay. Yeah, prediction.
So I agree with what you say, obviously, about the horror infinitum. But it seems to me that, if I understood correctly, your recipe to kind of diffuse it is to say, well, we can have infinities in the mathematics without supposing that we have infinities in the world. I'm not sure that this line of reply will work for like the nominalistic version of GR that I'm aiming to construct, which I think should be the best version of GR if it exists. So do you think there are other lines of reply? So for instance, to just refuse the positivistic assumption that everything that exists in the world ought to be measurable, or that, that we could, if there is a quantity, we should be able to measure it, rather than just believe it as an inference from things we can measure.
I like it. And you think that works?
Well, I'm not sure that, you should work out in principle exactly how, if you want to take the first line and say, okay, there is something, infinity in the mathematics, so you don't represent anything. I think that's maybe a standard line if you want to think that GR is an effective theory. But then you should explain exactly under what condition the mathematics ceases to represent, and that's not easy. Should you say, when various scalar curvatures start to get too big around the region, then in the manifold that this starts to not represent, you should work out this kind of examples. Another option is to, and I think this should be worked out independently, but there is a possible world in which, say, GR is the exact description of that world. I don't think that's something which is incoherent. And there, yes, I think the line is to say, yes, well, it's exactly described as GR. There's a logical inconsistency. There's only an inconsistency with positivistic prejudices about infinities in the world. And what do you think?
I like it. I don't really have much comment. What do you think? I think it fits with us. Yeah. Rather than saying that there's infinities in the world. So it would be kind of a response to Ellis and Co. in the same way that we had. Yeah. Okay. Yeah, okay.
So I have a clarificatory question and then a comment. My understanding of your argument about infinities is that they're not necessarily constitutive of internal consistencies, but there are cases where they do truly contribute to internal consistencies, and singularities in GR is one example of that. Because then you have determinism and indeterminism simultaneously as arising. Okay. And then a comment, whether or not you take that to be even an inconsistency for a subset of GR solutions, which the cosmic censorship hypothesis is supposed to diffuse at least on an empirical level, that we would never be able to observe such internal inconsistencies. I think that is a huge motivation for the development of quantum gravity, actually, with the black hole information paradox, because there the concern is, even with the cosmic censorship hypothesis, supposedly, you have this breakdown of determinism when black holes evaporate, and it's supposedly because the singularity acts as a sink for the matter that forms it in a way that it cannot be recoverable in the radiation. And so just to give you two examples of how it did inform the development of quantum gravity, so Ravelli used singularity resolution in the context of loop quantum gravity to explain why at the Planck scale the black hole will tunnel into a white hole through some quantum fluctuation process, and then the radiation will start to purify. That's one example. Another one is fuzzballs and string theory, where they just deny the interior of the black hole, and they eliminate the singularity that way. And so that's another context to redefine what a black hole is, so that the radiation can have all the information of what should have formed this quasi or pseudo black hole in the first place. So yeah, at least from this case study, it seems like there has been a lot of work in developing quantum gravity theories precisely to resolve that.
Yeah. But I would say in that case, the black hole information problem, that's not really internal to GR, right? It's coming from including other theories. Like, it's not from GR by itself, right?
I guess the idea is that it's imported from GR, that the classical black hole, if you hold on to the picture of a classical black hole in semi-classical gravity.
Yeah, exactly. Semi-classical gravity.
But that's
already
yeah. So in what sense are you asking about motivations for quantum gravity? I mean, is semi-classical gravity still a prior theory that can contribute to motivations for quantum gravity, or are you just looking at GR and quantum field theory?
Yeah, exactly. I mean, it was kind of the same with the other one where we were looking at the UV completeness, right? And that wasn't, it's already coming from kind of new theories that we're attempting,
Right.
I think it's really interesting. I guess I haven't worked it out, but that's exactly what I'm curious about. But yeah, is that internal inconsistency or external inconsistency? It's somehow coming from the way we're mixing and matching and attempting.
Exactly.
And then we end up with more problems, and then we take those problems as constraints. Yeah, it's really interesting. So yeah, it's a good point. How these can motivate and how they should motivate. Yeah. I don't know. It just seems like we're getting more flimsier and flimsier, you know, moving further and further away from the empirical aspects. Yeah. So you're right. We might need some more finer grained distinctions here. Yeah. Thanks.
All right. So next we have Enrico, Lucy, and Nick. And if I missed some of you, first I'm sorry, and please raise your hand again if you have an issue. Oh, you want to
My
make?
question was kind of a...
Okay,
yeah.
so please go ahead.
So, could you say that again? So that my question was sort of where are you drawing the line between
I don't know.
quantum gravity and QFT and GR?
Yeah. It does
Is that
seem
what you're
quite
saying, that
messy.
maybe you are putting semi-classical gravity on the quantum gravity side? But what then about quantum fields in curved space-time? I mean, I'm just going to have my black hole, and I'm just going to, okay, I've just got a Schwarzschild solution, so that's all GR, and now I'm just going to now sort of do QFT in that background. That surely has to be the regime of GR plus QFT rather than quantum gravity, right?
Yeah.
And I'm not sure you need to really like draw a line,
Yeah,
right? I
I
mean,
don't
you have
think
like these, heuristic kind of principles. So you have like the idea of avoiding inconsistency, either external, internal, and whatever. And you can like use the try to use this principle to you can apply that to all the different theories that you want. Like, I mean, suppose that we find like a theory of quantum gravity that kind of explain singularities and other stuff. But maybe it's not like the most fundamental theory we can find. So we can then apply like the same kind of reasoning on this theory to avoid possible inconsistency that we have in that theory to find another theory, a more fundamental one and stuff like this. So I mean, I think it's
We can
right.
still use them. As
I think it's
motivation.
exactly. It's more like about about like the heuristic and the this kind of distinction between external, internal, and empirical inconsistency. And like in this case, like the case study that we used were just GR and quantum mechanics, but then like actually, the distinction is more like fine grained and it's not so clear that you really have a line. It's more like kind of continuum. So you have like it's very, let's say, not singular theory, but like you keep something from the previous one and you add something from the other one, kind of, right?
Yeah, but it's still coming out as a, like it's somehow a product of our two theories being inconsistent that we're coming up with these problems. Yeah, so maybe it is external still. Or internal. Yeah, exactly. Then it doesn't make sense to label it like this.
I'm going to have to come back to this, but I think it's maybe the talk of motivation gets to be sort of strange, right? Because we have GR. I mean, we don't need any motivation to try and do quantum field theory in curved space-time if we think space-time is curved and we think there are kind of quantum fields. And I would say sort of similarly going further than that, certainly into semi-classical gravity, and here I kind of point you to Wallace on low energy quantum gravity. His whole point is we have that theory. It's we don't need any kind of motivation to sort of look for it. We have it and we use it in cosmology, in lots of kind of cases. That is the theory. So maybe I don't know. I don't know kind of quite how to sort of resolve that. You sort of have to actually talk about the inconsistencies. You already have to be looking at those theories that have been unmotivated otherwise. And I don't know. So maybe some of the different points just kind of applied in different ways. Because some of the time you're certainly thinking about motivations for a UV complete theory of quantum gravity, right? And sort of semi-classical gravity isn't that kind.
Right.
Does that make some sort of sense? And then, there's different things you're looking for motivation for, and different kinds of ways of putting GR and QFT together or separate.
I think that's really good.
But I really liked, to hear all these kind of arguments put together in this kind of list. I found this really kind of nice and helpful. But the black hole one, I think, needs to be on the list.
Yeah, exactly. I think that's a good point.
Right, Enrico?
Okay, thanks. I maybe wanted to ask you to go back a bit on the internal consistency of QFT, because if I'm not mistaken, you mentioned that the infinities that appear when you do perturbation theory in QFT, right? Those do not count as an inconsistency in your view, right?
Right.
Okay. And now the question that I had is that it seems to me that what the literature found in physics and philosophy is that they do not count as inconsistency. That's true. Exactly when you can do things like renormalization maybe, or you have some kind of story about effective field theory, even if the theory is not renormalizable. But no, the standard law in physics is that when you try to do QFT, but with general relativity, so you try to construct the QFT of the gravitational field, that is exactly the case where this explanation that allow you to basically ignore the infinities and ignore this inconsistency and treat this inconsistency, they stop working. So, is it the case that maybe the QFT is inconsistency exactly in the case of gravity, and this is the motivation maybe that is pushing people to try to resolve this, to try to find a deeper way to solve these problems instead of just renormalizing them away?
I mean, there's different explanations for this. Most of them think that it's from the perturbative picture, right? And then it might motivate a QFT rather than QG.
Yeah, but the thing is that, if I'm not mistaken, and I might be here, when the thing is that there are you could of course do a QFT, but the result would be that you would have an algebraic quantum field theory of the gravitational field, and that would presumably be just quantum gravity, right? So the thing is that when you do gravity in this way, you just can't, you cannot cure them as you do with the standard model, for example, right? Because the divergence is too bad.
So this was maybe related to the paper with Niels we wrote about the lack of UV completion in
if I jump in here.
Yes, please.
So GR as a Q of T is normally seen as effectively renormalizable, right? So effective field theory. And but you could say that up to a certain energy level, you just need a finite amount of information, so to speak, to fix the infinity, so to speak, up to that energy level. But from then on, basically, you would need infinitely many, infinite amount of information, so to speak, infinitely many measurements. And then you could wonder, is this a real inconsistency of the world, or is this more a practical indeterminability, so to speak, right? And just purely metaphysically, I think in our paper, when we take the stand that it might just be, I'm actually a bit skeptical here, but that might be just seen as a huge issue of undetermination, so to speak, in practice or epistemically, but not necessarily that the world as such is not well defined. And so maybe one line you could take why you don't want to call perturbative GR inconsistent, namely because you're saying from a logical point of view, even though it's just an effective field theory, the world can still be determinate, so to speak.
Can I just maybe ask a small follow-up at this, or be short answer? Okay. But I mean, fair enough. Yes, that's true. Would it be the case, however, that these infinities that you find, they would come up in like technically stuff that you're supposed to measure at the appropriate energy scale, right? Like scattering out with the graviton. And that would be large.
Yeah, the thought is more, I mean,
if
you gave yourself the possibility to measure infinitely many coupling terms, so to speak, then you could even get rid of these infinities. But I can understand the skepticism here that this might be a bit far-fetched, but that's why, however, I can make a distinction between being practically epistemically undeterminable as opposed to whether the world itself is indeterminate. It's just not a consequence out of mere non-renormalizability that therefore the world is undeterminate. It's in kind of Aristotelian sense, so to speak, contradictory or there.
Okay.
Right, Lucy?
Yeah, just a curiosity really. I'm also interested in this issue about infinities, but it's not something I know much about. So, fair enough that infinities may not imply inconsistency, but it's still a feature of the theory and the interpretation. You kind of skipped really quickly past the Penrose stuff on that, so I was just wondering if you could say a bit more about what strong cosmic censorship is and how that plays into it.
On how it solves it. Just that we can't, that it doesn't lead to an inconsistency where we have indeterminism and determinism at once.
What is strong cosmic censorship?
I'm not a super expert on this either. I mean, when I first started reading about it, I was thinking more like weak cosmic censorship, like, it's hidden behind, and Dihara and I were both thinking, it's hidden behind the event horizon, and we don't see it. But then we're thinking, well, that doesn't solve it because it's still there, even if we don't see it, right? The strong cosmic censorship is something different. The relevant horizon isn't the event horizon, it's this Kachu horizon. And that's where you have the indeterminism. So if that doesn't appear, then you're not going to have the problem with determinism. So it's just the, saying that this doesn't occur, and then we'd never be able to detect it.
Okay, good, thank you.
Me?
Finish reading that.
Oh, sorry.
Yeah.
I'm just reading, don't worry.
Oh, yes, right.
Okay. So this is kind of carrying on from what I was actually, and then what I was asking sort of earlier to sort of think a bit more about, so suppose we have kind of pushed things to semi-classical gravity, as a way of sort of thinking about how we could have GR and quantum field theory, sort of without going to full quantum gravity. And then, sort of a few things I guess I wanted to sort of just point to in case they were sort of helpful. So one is the sort of tradition of arguments that purport to show that you can't have semi-classical gravity is sort of inconsistent in some way. So there's the sort of Epley and Hanna arguments that Craig and I sort of attacked, and Chris has worked on, and that train. And then, but there's also more recent work by various people. Wald is sort of at the centre
I
of
emailed
this.
Curiel before I came here, and he sent me stuff, but I haven't read it yet.
Yeah.
But yeah, he got all of these different issues with it, right?
So there's some quite nice, some quite nice arguments there that you can't have sort of if you have sort of semi-classical gravity like that, you're going to have to either violate causality or complementarity. I mean, for me, it seems if you've got GR, well, you probably are going to be violating complementarity. But then that's sort of then I thought that was the kind of question I had for you. If I have quantum mechanics, but I have some classical variables, so I can actually now violate, the uncertainty relations by playing with the classical part of the theory. What kind of inconsistency is that? I mean, in some sense, it's inconsistent with quantum mechanics, but maybe you've kind of mushed them together in a way, but maybe it's not really. And then finally, I guess a plug for this tabletop quantum gravity stuff, which seems like if this experiment, I think, absent some sort of, it seems to me really pretty close to, if they do I won't go into the experiments, they're trying to do these experiments, and if the predictive effect is seen, it's well nigh impossible to think that there's GR and quantum mechanics. In quite a strong sense, you really will have to have something like superpositions of quantum superpositions of gravity. So anyway, that's just pointing you to sort of something that I think, because I think this is great, but there's like a book here or something.
That was still going with the GR and QM instead of going to the actual theories that people are using now. Yeah, good point. And I think it's really, really interesting in that respect too, because here we are, exactly, trying to construct a new theory that, we're doing it because we expect our current theories aren't correct in some respects. So then, of course, the new theory is going to contradict them in some respects. How much consistency do we need to get back, right? Maybe it shouldn't be such a strong constraint.
Yeah. I think I'm partly sort of, these arguments, it's actually kind of nice to think of all those arguments sort of in the context of the kind of discussion you're having. I think I find that kind of helpful for thinking about what those people are saying.
Yeah, that's cool.
And they're not always totally clear about what it is that the upshot is. And I think this is sort of a helpful way.
Thanks.
Right, Sam?
So one of the moves I think that you made was with respect to the external inconsistencies, saying something like, well, don't be a naive realist about those things, and that'll enable you to dodge them. I guess I just wanted to press you a little bit here, because I think those external inconsistencies are going to show up in the chunks that even a sophisticated realist might want to be realist about, right? So sometimes you're going to find that. Here's one version of realism where it's going to do this. So some scientific realists are going to say, just be realist about the explanatory bits. There's lots of cases, I think, where the explanatory bits are going to come up with inconsistencies that are going to conflict in the external sense as well. Just think of like a phase transition thermodynamic type situation where you have to assume there's an infinite number of molecules there to get the critical effect. And it's explanatory, right? So it's kind of, you can't want to be realist about that chunk, but you can't see. So the naive realist, it just feels like a little bit like you might need to dig into some of the realist approaches there as well.
What do you think on this?
Well, actually, in thermodynamics, when you say when you have infinities, you don't actually mean like an infinite number, right? You mean like a very, very extremely big number. So it's not. So in Ali's paper also, this was the distinction between, well, I don't remember the label, but it was like, actual infinity, so it's really like infinite, and then you have like infinity in the sense of unmeasurable, like very big numbers. So like in a sense like empirically unmeasurable, but like still, in some sense limited. So it's not what you actually mean when you have.
Sure. I mean, even if it isn't the case in the thermodynamic example, like water wave analysis gives you in the oceans infinitely deep. Like there are lots of different cases where you make these assumptions about the world being infinite in some sense, and it's like in the explanatory chunk of the theory, not the bit that you might be realist about.
Sure, but in those kind of cases, like we have kind of external access in other theories to know that there aren't actually an infinite number of molecules in your kettle. But like, if we're talking about, I'm going like full here, like why can't we have infinity in nature?
I'm not bothered by having infinity in nature. All I'm saying is that like naive realism doesn't get you out of the problem that you like just moving away from naive realism doesn't get you away from having to deal with these external inconsistencies. That's the only point I'm making. I don't have a problem with nature being infinite, massively inconsistent. That's fine.
Timeless.
Timeless. Yeah, like just think of an implausible view.
It's true. Yeah. Okay, that's a good point. So we need to maybe modify this one. Here, explanatory. Yeah. I mean, that's the interesting thing too. Like, if it could be some actual infinities in nature, and yet we reject infinity as being unscientific. Like, maybe that's just the part of philosophy, and the fact that we can't ever test it means it shouldn't be part of our science. But anyway, yeah, your original point, I think.
Yeah, it was just about naive realism.
Yeah.
It's not going to get you out of it.
Yeah, true.
Right, so that's the end of the queue of questions, I think. So maybe it would be nice to stop here, so we are on schedule again. So I would suggest we just stop here and continue.
Linguistic notation.
Okay.
That Emilia noticed, and we Italian with classical building, it's not horror infinitium, but infinity.
Oh.
Where do you have this?
I don't know, I just went to Google Translate Latin.
Latin escapes, that is the tricky part. Latin escases, that is the tricky part. You might have translated infinite.
Okay, can you write it down?
But you have horror of the infinite, which is different.
It's a genitive.
It's infinity.
Thank you. Alright, we need to write this.
I did Latin in high school actually. That's my fault.
Card revoked immediately.
What?
Nothing.
Alright, so Emilia wants to ask the last question?
Yes, it's just a clarificatory question. When you were discussing about internal inconsistency in QT, you mentioned this Hack's theorem, and I was wondering whether you could expand a bit on that.
That I cannot. I have not looked into it at all.
Okay.
But yeah, checking these papers, it's been quite discussed, for instance, by Doreen Fraser, James Fraser, and Michael Miller has written one. Those ones are the ones I would recommend.
Okay.
From my cursory readings of them.
Some old stuff by John Irwin.
And there's more?
Fraser
Okay.
and,
Fraser and yeah. Yes.
Yeah.
He said Laura Ritchie. In her book, I think also.
Also? Okay, yeah. So I should look into
Yeah,
that.
Doreen's whole dissertation.
But do you have an idea of where the inconsistency among the set of principles as discussed by
No, that's basically, I think I just took this actually from Doreen Fraser. Where did it go? I went past it.
Yeah.
Again, we passed it.
So,
Yeah, like this is how she lays it out. Like, we have this assumption and then you have this and then we have the contradiction.
but it's a theorem. So it's a theorem in axiomatic quantum field.
Okay.
So you write down your favorites, Hog axioms, or Leibniz axioms, and prove.
Again, it's a question whether it's an internal consistency or inconsistency, because that depends what exactly you take to be Q of T.
Yeah.
If you take to be Q of T to be the axiomatic case of Hobbes' theorem, there's no internal inconsistency, but it seems in some way external or empirical inconsistency, because we know the world is not free, there are interactions. So that's kind of a reductio, but only vis-a-vis what we take as given from the empirical side.
Yeah, that's a good point too. The empirical part. Yeah.
Thanks.
Right, let's have lunch. Thanks again.